Okay, for this video, I'll be going through pure physics pressure tutorial. Question 1, an empty measuring cylinder has a mass of 60 grams. So this is the mass, M. Now, when it is filled with 30 cm cube of olive oil, the total mass is 87.6 grams. So this is the volume of olive oil. They want us to calculate the density. Okay, so in order to find the mass of the olive oil, I need to take the final mass, subtract with the initial mass, which is the mass of the measuring cylinder, so it will be 27.6. okay, so I have 27.6 grams and the volume is 30 cm cube. The density formula is density equals to mass over volume. So I have my mass, I have my volume, and the answer will be B. Okay. So before you convert your units, or you need to pay attention to the units. If it's for MCQ, you see that everything is in grams per cm cube, so you just leave everything in grams per cm cube. There's no need to convert. Question 2, an experiment was conducted to determine the density of pine wood. Okay, the mass and volume of different pine wood samples were measured, which graph shows the correct result. Okay, so because density equals to mass over volume, okay, and if you look at any of the graph, actually all four have the same axis. So the mass is the y-axis, the volume is the x-axis. Okay, so that makes our mass the y-axis and the volume the x-axis. Okay, so if I were to find the gradient, it will be your mass, change in mass over change in volume. So basically the gradient of this mass versus volume graph, okay, is equals to the density. Okay, and we know that density will not change, right? Because if whether it's half the size or the full size, the density of a pure object will not change, right? So we are looking for the graph with the same gradient or the same density. So for D, it is out straight away because the gradient is 0. So if the gradient is 0, it means that the density, right, is 0. So D is out. It cannot have 0 density. C is also out because it shows that the gradient is negative and we cannot have negative density. Alright, so now it left with A and B. Okay, so it is actually, if you do it in math form, y equals to mx plus c, right? You will see that the y is the mass equals to the gradient, which is the density, okay, multiplied by the volume, and there is no y-intercept. There is no y-intercept, right? Because based on this formula. So therefore, the C is 0. So therefore, answer is B. But if you think of it another way, right? If this the way of solving is too mathematical for you, you can think of it as, can you have mass without volume? Which you can't, right? Whichever volume that you have must have a mass. So in A, it seems that when the volume is 0, there is a mass. Okay, there's a mass. That means it is not correct. How can you have a certain mass when the volume is 0? It's just not possible. Okay, so answer is B. Okay, question 3. A cube of volume 0.080 meter cube in SI unit is made of material of density 200 kg per meter cube. So we see that the units tally. So calculate the mass. So you just substitute in, you get 16 kg. There's no tricks about the unit. No need to convert anything. Now weight of the cube, W equals to mg. So because this is already so W equals to mg is a SI unit formula. Okay, and because our mass is already in kg, just multiply by the gravitational field strength and you should get 160 Newton. Okay, in figure 4.1, a beaker containing 60 cm cube of liquid weighs 0.8. So this is the weight or the force, and this is the volume. Okay, take note that it is in cm cube. Now, a stone is immersed in a liquid. The new weight of the beaker and its content is 1.24. That means the weight of the stone is equals to 1.24 minus 0.80, so equals to 0.44 Newton. Okay, and the liquid level rises to 80 cm cube mark. That means the stone's volume of stone equals to 20 cm cube. Okay, they want us to calculate the density of the stone. They didn't say whether it need to be in SI unit or not, but because the weight is given, which is in Newton, so I can actually find the mass of stone. Okay, because W equals to mg, so mass is equals to W over G, right? So equals to 0.44 over 10 equals to 0.044 kg. Okay, so because they didn't specify whether we want to leave it in SI unit or not, I can actually convert this to 44 grams, which is actually simpler for me. Okay, so since I now have the mass, I have the volume, the density will just be mass over volume, so it's 44 over 20 equals to 2.2 grams per cm cube. Okay, so you can either express your density in grams per cm cube or kg per meter cube, right? But there is no such thing as, in our syllabus, they won't ask us to express it in kg per cm cube or grams per meter cube. Okay, so usually it's either kg per meter cube, SI unit, or gram per cm cube. Okay, so if you would like to then convert your answer to SI unit, it will then be 2.2 multiplied by 1000 equals to 2200 kg per meter cube. Okay, so from grams to cm cube to from gram per cm cube to kg per meter cube, you multiply by 1000. You can memorize this, but if you want to do the hard way, you can keep your mass in kg and then you convert your volume to meter cube. So you have to take 20 divided by 100, a total of 3 times, right? Because from cm to meter you need to divide by 100, but now this is cm cube to meter cube, so you need to divide by 100 3 times. Okay, so whichever way you want it, and also depends on what the question is asking. Okay, now explain why this method cannot be used to determine the density of solid ash. So if we look at solid ash, right, it is actually floating, right? So we cannot determine the volume. Okay, we cannot determine the volume because it's not fully submerged. Okay, question 5. In an experiment to determine the density of paraffin, the following readings were obtained. Okay, question 5. In an experiment to determine the density of paraffin, the following readings were obtained. Mass of an empty bottle, 32.20 grams. Mass of the bottle filled with paraffin, 73.10 grams. So I can know the mass of paraffin to be 73.10 minus 32.20. Okay, equals to 40.9 grams. Okay, and now if I change the content of the bottle to be water, okay, I have mass of water to be 83.2 minus 32.2, so equals to 51.0 grams. Okay, so this is what is being done here. Okay, and they want us to calculate the density of the paraffin and assume density of water. So now that we have the mass of the water, we have the density of water, which is over here. We can actually then find the mass of water. Okay, so the mass of water will then be we can then find the volume of water inside. The volume, I'm sorry, because we have the mass. Okay, we have density, we have mass of water, we have density of water. We can then use it to find volume of water. Okay, so we get 51 cm cube because the mass is 51, the density is 1 gram per cm cube, same units, grams. We have the volume of the water to be 51. That means the volume of the bottle is actually 51 cm cube. Okay, so then if we now know the volume of the bottle, which means it is the volume of the paraffin, okay, we can then get this calculation. So again, take note, if you want to convert from gram per cm cube to kg per meter cube, you multiply by 1000. Okay, so now we go into the pressure part. Okay, a water jet applies a pressure of 20 megapascal, which is P equals to 20. Mega is 10 to the power of 6 Pascal. Okay, and Pascal is the SI unit for pressure on an area of 5 mm square. Okay, so this is the area, but the trick here is that the area is not in SI unit. So although pressure is in SI unit, area is not, so we have to convert your area to SI unit. Okay, so area is 5 mm square. So to convert mm to meters, we need to divide by 1000. Okay, or from prefix to no prefix. Okay, which is from mm having prefix to meters no prefix, we multiply by value of prefix. Okay, so you have to be very used to all these prefixes because they are now in every chapters. Okay, so from prefix to no prefix, we have to multiply by the value of prefix. Okay, so this is the rule that I use, and the value of prefix of milli is 10 to the power minus 3. Okay, 10 to the power minus 3. That means I need to take my 5 mm square, I need to multiply by 10 to the power minus 3, and I have to do it again because now it's mm square. Okay, so therefore I have this working over here, and I will get a force of 100 Newton if I apply the formula pressure equals to force over area. Okay, so that's for question 6. Question 7, a submarine is resting on a seabed at 80 meters below the sea level. Density of seawater is 1025 kg per meter cube, and atmospheric pressure is 1 times 10 to the power of 5 Pascal. Take G to be 10 Newton per kg. They want us to calculate the pressure acting on the outer surface. So now we are moving into liquid pressure, and in my notes I did say that if you have any surfaces where gas, air, or atmospheric pressure is acting upon it, you need to draw a downward arrow. Okay, and then label it as PATM. So the hatch is over here. I also have liquid pressure exerting on the hatch. So basically it is PATM plus the liquid pressure of 80 meters above it. So the formula is pressure for liquid is rho GH. I have the density, which is 1025. I have the G, which is 10, and I have the height of 80 meters. Substitute everything in, okay, into this, and on top of that, I also need to add in my atmospheric pressure because it is acting on the liquid surface, and this adds on to the pressure experienced by the hatch. Now, if the hatch of the submarine has an area of 0.5 meter square, okay, so because this is in meter square SI unit, okay, later we don't need to do any conversion. We need to calculate the force acting on the outer surface of the hatch, which is F. So we use formula P equals to F over A. So bring A over, so F equals to P multiplied by A. So the pressure we can use from part A, which is 920,000 Pascal, okay, multiplied by area of 0.5. So we'll need a force of 460,000 newtons. That is quite a lot. Okay, so basically it is very difficult to open up the hatch because you are moving. You have to apply this much of force to fight against the pressure that's acting on the external. Now, the outer surface of the submarine can withstand up to 30 atmospheric pressure. Calculate the maximum operating depth. Okay, so the maximum pressure on a submarine that they can exert is 30 PATM. Okay, and there is only one PATM acting on the liquid surface, right? They mentioned right at the start, right? Is 1 atmospheric pressure. Okay, 1 PATM. So basically, the submarine outer surface can withstand a maximum of 29 PATM. 29 PATM, right? So, and 29 PATM, it must be equal to the height of the liquid above it. Okay, so once again, we use the density of the seawater, we use a G, we are going to find the maximum operating depth, which is the height of liquid above it. Okay, and it will account to 283 meters. Okay, 283. Okay, question 8 illustrates the braking system of a car. The master cylinder and its pistons are connected hydraulically to a slave cylinder and its piston. The thrust, which is actually a force on the piston in the master cylinder, is 600 Newton. So this is the master cylinder. Okay, the thrust is 600 Newton and the cross-sectional area is 3000 mm square. So again, this is not in SI unit. So we have to calculate the pressure in the hydraulic press. We use pressure equals to force over area. Now the force exerted on the master cylinder is 600 Newton. The area is 3000 mm square. Convert to SI unit, important. So you should have 200,000 Pascal. So calculate the force on a piston in a slave cylinder. Okay, because this is hydraulic press and the change in pressure in enclosed liquid will be the same. In enclosed liquid will be the same everywhere. Okay, so this change in pressure will be experienced by the slave cylinder. So now we know the pressure at the slave cylinder is equal to force that is at the slave cylinder and the area. Okay, because the cross-sectional area is now larger, so but we take note again that it is in mm square and not in SI unit, so we have to convert it to meter square. That's why we need to multiply by 10 to the power minus 6. How do I get 10 to the power minus 6? 1 mm to convert to meters. Okay, I have to multiply by 10 to the power minus 3. From prefix of milli to no prefix of meters, okay, I have to multiply by 10 to the power minus 3. But now it is 1 mm square. I need to convert it to meter square. So I need to do this operation 2 times. Okay, 2 times. So 10 to the power minus 3 times 10 to the power minus 3. You must have learned your indices. So it becomes 10 to the power minus 6. Okay, so that's why this 10 to the power minus 6 appears here. And then you'll find that this pressure is exerted over here at the slave cylinder multiplied by area will get a force of 1800 newtons. So although we exert a force of 600, okay, because due to this hydraulic press design, okay, by having a larger area at the slave cylinder, I am actually able to have a larger force. Okay, but is this really possible in real life? Yes, because let us now calculate the distance moved by the piston in the slave cylinder when the piston in the master cylinder moved by 30 mm. So this one will also be covered in the chapter of energy. Okay, maybe you can come back and talk about it. But to solve it now, you see that when you are exerting a force, right, on the master cylinder, the volume of liquid move, right, will be equals to the volume of liquid that is being moved by in the slave cylinder, right, because they are all connected. It's in an enclosed liquid. Okay, so that's why I have volume in slave cylinder, okay, that is being moved will be equal to the volume moved in the master cylinder. Okay, and volume is equals to area multiplied by the depth or thickness, if you like. So the area of the slave cylinder is 900 mm square. Area of master cylinder is 3000 mm square. Okay, and because it was moved by 30 mm, so that's why I keep it as mm square, and anyway both sides we are using the same unit, so there's actually no need to change it to SI unit. So you work it out, the distance moved by the slave cylinder is 10 mm. So you see, even though the the force exerted by exerted at the master cylinder is 600, and the force exerted at the slave cylinder is 3 times of it, the distance moved by the master cylinder is only 1/3 of the distance. Sorry, the distance moved in the master cylinder will be 3 times the distance moved by the slave cylinder. Okay, so you compare, this is 30 mm square. 30 mm is moved by 30 mm, sorry, not 30 mm square. Over here is only moved by 10 mm. Okay, because even though the force is smaller, the distance moved is larger, and at the other end the force is larger but the distance moved is smaller. This is actually your work done equals to force times distance moved. Okay, you multiply them together, you will get the same value. This is in line with the principle of conservation of energy. Okay, now part D, then explain the effect on the braking system if the air bubbles are trapped in the hydraulic oil. Assume that the thrust exerted on the foot pedal remains constant. Now the force acting on the brakes will be smaller than expected, right? Because air is compressible, so we will have to do work to compress the air bubbles, right? Because now there are air bubbles present, so therefore the pressure will not be transmitted equally from master to the slave cylinder. Okay, question 9, using Pascal principle, which is actually the principle that we use in for liquid in a enclosed container, enclosed liquid. Describe how a force applied at the brake pedal in figure 9 will lead to the braking of the car wheel. Okay, so we start with the driver, okay, applying a force on the brake pedal, and it pushes the master cylinder. It applies a force. He applies a force over an area, so there will be a change in pressure, right? And this change in pressure will be experienced equally in all parts of the liquid, right? Because this is Pascal's principle. So the force applied at the master cylinder exerts pressure in the liquid fluid. By Pascal's principle, the new pressure is transmitted equally throughout the confined fluid. Okay, now the pressure exerted on the brake piston, which is over here, okay, will result in a force which pushes on the brake lining, and the brake lining then applies a frictional force on the brake drum, okay, to stop the wheel from moving. Okay, so maybe this part you are not so familiar, right? But this part you should know. Okay, this is Pascal's principle. Okay, figure 10.1 represents a simple mercury barometer, right? Barometer. The other one is manometer. They are different. Okay, so barometer will measure atmospheric pressure. Okay, the scale alongside the barometer is marked in mm. Take note, not SI unit, so maybe we need to convert. Now state the pressure in mmHg at the following points in figure 10.1. So 10.1 we have A, B, C, and D. Okay, so what is the pressure at A? Is 0. Why? Because this is a simple mercury barometer. They didn't tell us that it's ideal or not, but we can assume that it is vacuum over here. So if it's at a vacuum, then there won't be any pressure on it, on the liquid. So at point A, the pressure is 0 mmHg. Okay, let me explain mmHg. I already did that in my notes. Mm is the height. Okay, the height of the liquid above it. So obviously at A, there is nothing there. So the height is 0. And the Hg is actually talking about the liquid that is being used. Okay, the liquid used in the barometer. Okay, and in this case it is mercury in your periodic table, it is Hg. So we are not just using the mercury, we are using the density of Hg. Okay, so we have H, we have density. Where is our G? The G is not included here because actually everybody stays on Earth, so there's no need to talk about the G. If not, I'll have to say the pressure in mm Hg. But when later on, if I were to ask you to convert this to Pascal, you will have to by your own self include the G, which is your 10 Newton per kg on Earth. Okay, but let's continue with this first. So A, because there's a vacuum on top, so therefore it is 0 mmHg, no pressure. At B, we need to find what is the height of the liquid above it. So basically it's 800 minus 400. So how many mm of Hg is on top of it? 400 mmHg. For C, it is, this is 0, this is 100, this is 50, this is 150. Okay, so we take 50 versus 800, so it's 750 mmHg. For D is 800. So at D, it actually has the highest pressure. Now state the atmospheric pressure. Atmospheric pressure is acting on this liquid surface, so it is equals to C, so 750. Figure 10.2 show the correct level of mercury inside the tube after pouring more mercury. Okay, even though you pour in more mercury, it is still talking about the relative height, or the height of the liquid level above the above the surface where PATM is acting on. Now PATM, they didn't change. Now what has changed from figure 10.1 to 10.2 is that more mercury is filled, and therefore this level goes up. So I must be able to get 750, okay, for this height. Okay, so we started off at 150. This is the level here, 150. So I need to add the 750 for the atmospheric pressure. So in the end, I ended up at 900. Okay, now figure 10.3 shows the correct level inside the tube after tilting the tube from position in 10.1. Okay, so we have to look back at 10.1, and you know that even if I tilt it, it will still go to the height of 750. Okay, so tilting doesn't change the atmospheric pressure. Now, suggest one way the barometer could be altered to make it more sensitive. That means you want to be able to measure very fine division. Okay, so we can actually replace the mercury with a liquid that is less dense. Okay, so what happens if I use a less dense? In our notes, we actually use water. Water has a density of 1000 kg per meter cube. For mercury, it is 13600 kg per meter cube. Okay, so that means I would have a longer or greater height of liquid of water, right? If I were to replace mercury with water, and therefore if I have a longer length, I should be able to measure more sensitive changes or more minute changes in the atmospheric pressure. Okay, question 11. It shows 3 mercury barometers that are placed at the base and the summit of Mount Everest. Summit means the top. Okay, take the density of mercury to be 13600 and density of air to be 1.25. Okay, water, by the way, is 1000. So the water's density is about 1000 times greater than that of air. Okay, so the more you're exposed to the densities, the more you can sort of remember, okay, or memorize. But actually you don't really need to memorize. By right, the question should give you. And just as a practice, in grams per cm cube, you divide by 1000, okay, and vice versa. Now determine the atmospheric pressure at the base of Mount Everest in figure 11.1. Leave your answer in SI unit, so we have to leave it in Pascal. So to solve liquid pressure, we always first step draw a downward arrow arrow on the surfaces that are subjected to air, gas, or atmospheric pressure. In this case, because it is an ideal or full working barometer, so there's vacuum inside, okay, so there's no pressure, so I only need to draw arrows here. And what is acting on it is the atmospheric pressure, okay. So the second step is to then determine where's the same liquid, same level, same pressure. So over here is where we have same liquid, same level, same pressure. Within the tube, it is due to this 84 cm worth of mercury. Outside the tube, it is atmospheric pressure. So therefore, atmospheric pressure equals to the height of liquid above it for this level, whereby we have mercury acting on it. So we have 13600. Because we have to, this is, by the way, a SI unit formula. The height is 84 cm, so I have to divide by 100 to get it in meters, and G is 10. And therefore, I'll get this answer, 114000 Pascal. Okay, 3SF. Okay, now in figure 11.2, some alcohol vapor is introduced into the barometer tube at the base. So the height of the mercury level in the tube above the reservoir becomes 70 cm. Calculate the pressure of the alcohol vapor above the mercury in 11.2. That means some alcohol vapor managed to sneak in. So instead of vacuum, like in figure 11.1, now we have alcohol vapor acting above the liquid. Okay, unlike figure 11.1 where we only have vacuum. Okay, but PATM remains the same, right? So again, we draw arrows, down arrows, to show where the liquid is subjected to either air, gas, or atmospheric pressure. So that's the first thing. Then next thing, we need to determine a suitable level where we have same liquid, same level, same pressure. So let's do the inner tube first. Inner tube is alcohol vapor, the pressure due to alcohol vapor, plus 70 cm of Hg. Okay, and it is equals to our PATM. Okay, our PATM just now we calculated was actually equals to 84 cm Hg, right? So we have PAV, alcohol vapor, plus 70 cm Hg. So therefore, the alcohol vapor will be equals to 14 cm Hg. Okay, but if you are confused by this, you can just work it out, but this is just a neater way lah. Okay, so if it's 14 cm Hg, this is the height, right? I need to multiply, this is the height, 14 cm, I need to convert it to SI unit. This is Hg, which is the density of mercury, so it's 13600, and what is missing is, very important, your G of 10, okay? It is not included in your 84 cm Hg or 14 cm Hg. But if you were to have to calculate it into Pascal, you need to include your G. Okay, so a lot of students, sometimes they don't add in the G, so their number will be 10. Yeah, their answer will be 10 less than the correct answer. Okay, so in the end you'll get 19,000 Pascal. Okay, part C, assuming that the density of air between the base and peak of the mountain is constant, calculate the height of Mount Everest. So we are now looking at figure 11.1 and 11.3. 11.1, it is at the foot. Okay, 11.3 is at the summit. Okay, so we see that actually the atmospheric pressure at the top, at the summit, okay, is actually only 2 cm. That means the air pressure up there, or atmospheric pressure up there, is very, very low, equivalent to 2 cm. So how do we find the height of Mount Everest? So if I take the height in the liquid level, okay, I can actually find the difference in the pressure, difference in the mercury pressure, and this will be equal to the difference in the air pressure. Okay, because if they are at the same height, then there won't be any difference, but now there's such a big difference of 0.82 meters. Okay, so with that, then I can confirm that over at the top there is very little air, and if I were to then use my rho GH to equate it to the difference in the mercury pressure, I have my density of air, I have my G, I can then find the height of air above. Okay, so I will get 8920 meters. Please try it. Okay, question 12. A student stands on a sail bag which is attached to a manometer. Manometer is your U tube. So it actually measures difference in what you call that? Difference in pressure. Okay, difference in pressure. So the manometer is filled with mercury. The air in the silk bag is initially at atmospheric pressure. Okay, so this is atmospheric pressure. Okay, draw the arrows. Over here also atmospheric pressure. Okay, then take density of mercury as 13600. So this is my rho. Now state the additional pressure exerted due to the student's weight. So initially, if the student doesn't step on this bag, the U tube should show equal level, right? Because the bag is also at atmospheric pressure. The outer tube, which is open to the air, is also atmospheric pressure. Okay, so they want us to leave our answers in CMHG. Now that the student has stepped on it, the pressure on the left hand side, okay, pressure on the left hand side is actually greater than the pressure on right hand side. Greater than pressure at right hand side, right? That is why this amount of liquid rises up. Okay, or you can say that same liquid, same level, same pressure. Over here is PATM. Okay, so the pressure at the left hand side is equal to the PATM plus this height of liquid. So the additional pressure is 30 cmHg. Okay, hence calculate the student's weight. Now 30 cmHg equals to rho GH. Okay, we have to find in terms of Pascal. So we have to add in our G, which is 10. Okay, so this 30 cm, let's do this again. This 30 cm is actually the height. This Hg is actually the density of mercury. What is missing is actually the G, right? So again, emphasize on the G. So also take note that your units must be in SI unit. So my 30 cm, I have to convert to 0.30 meters. So the most common mistakes for this kind of question is, number one, students forgot about the G. Number two is SI unit. They didn't convert it to SI unit. Okay. And sometimes they don't draw the arrow, so they may omit some of the pressure exerted on some surfaces. Okay. So the student's weight, after we found out the additional pressure due to his weight is 40,800 Pascal, then you use the formula, you should get 918 Newton, and his mass is actually 91.8 kg. Quite a big value. Okay, question 13. Manometer contains water and unknown liquid. The two liquids do not mix. Okay, given that the density of water, okay, is 1000 kg per meter cube, calculate the density of the unknown liquid. This is the unknown liquid, so this one is the unknown liquid. Okay, and you can see that the density of water is greater than density of unknown liquid, because you see, for water I only need 16 cm, right? Applying same liquid, same level, same pressure, yeah. Same liquid, same level, same pressure. For the water, I only need 16 cm versus 20 cm of the unknown liquid. So the density of water must definitely be greater than the unknown liquid. So we'll use this to check our final answer. Okay. So apply same liquid, same level, same pressure. Because both sides we have PATM, right? So I don't need to add in for both, right? So I can just do the water part, 0.16. Again, change it to SI unit. The density already in SI unit, kg per meter cube. Our G is 10. Then over here, 20 cm cube. Again, change it to SI unit. unknown liquid's density multiplied by 10. So you get 800. And 800 is less than 1000. So our first check from the diagram, it is correct. Okay. Okay, question 14 shows a mercury barometer and a manometer, right, containing water connected to a gas supply, placed to a meter rule. Take density of water to be 1000 kg per meter cube. Good, that is in SI unit. Density of mercury to be 13600 and G to be 10 Newton per kg. They want us to calculate the atmospheric pressure. Okay, so atmospheric pressure is can be measured from the barometer. Okay, so if this is a working barometer, inside here is vacuum, so we don't have to draw arrows, but atmospheric pressure is acting on the liquid surface outside here. Okay, so where do we have the same liquid, same level, same pressure? Over here at this level, same liquid, same level, same pressure. So PATM is the pressure in outside of the tube. Over here will be due to the liquid pressure, which is also equals to PATM because of same liquid, same level, same pressure. And then we can get our readings from here, from the meter rule that is placed over here. Okay, so the height is actually 73 cm. Okay, so applying rho GH, our density is 13600 because this is mercury. Okay, G is 10, H is 73. Okay, I can't really read very well. I need to convert to SI unit. So in the end, I should get 99,300 Pascal. Okay, now calculate the pressure of the gas supply. So now we move on to the U-tube. Okay, so again, first step, whenever there is pressure acting on surface, in this case, here is PATM. Over here will be the gas pressure. Okay, so now we have to find the gas pressure because U-tube finds the difference in pressure. Okay, so again, where is same liquid, same level, same pressure? Over here, this level. Okay, so on the right hand side is P gas, which I'm supposed to find is equals to PATM on the left hand side plus this height of liquid. So again, this height is 80 cm versus 30 cm. Okay, so it will be equals to 50 cm Hg because both are filled with mercury, right? So PATM we have already calculated is 73 cm Hg, right, plus 50 cm Hg equals to P gas. Therefore, P gas is actually 123 cm Hg. Okay, so if it's 123 cm Hg, then we convert it to 1.23 times, because change it to meters, right, SI unit, times 13600 times 10. Don't forget the 10. Okay, and because this working is slightly different, let me test 1.23 times 13600. So I get PATM plus P. Oh, I'm very sorry. So what is actually inside here is water. I did not read the question. Okay, so in the manometer it contains water, in barometer it contains mercury. So I was tricked by this. So I can't actually add them up together. Okay, so I have to redo everything. This is 50 cm water. Okay, so I should just use my 99,300 plus 0.5 times 10 times water's density to be the P gas. So again, my answer is different. My working is different from this, but I'm going to try it again. This will be 5,000 equals to P gas. So my final answer will be 99300 plus 5,000 equals to 104,300. In the end, works out to be 104,000 Pascal in 3SF. Okay, so it's the same as this. Okay, part C, assuming that the gas pressure in the container now increases by 30 cm of water, on figure 14, mark the new position of the two water level in the manometer. So they are looking for manometer and they want it to mark it in figure 14. So I have to make sure that I mark correctly. Okay, they say that the gas pressure is increased by 30 cm. Just now the difference, the gas pressure is actually 50 cm. No. Okay. The gas pressure is the atmospheric pressure plus 50 cm of H2O. Okay, but now it is further increased. That means it is now PATM plus total 80 cm of H2O. Okay, but although the increase is by 30 cm of water, right, I cannot just say it went from 80, it doesn't go from 80 to 110 because I need to take the difference in height. So I need to use this trig 30 divided by 2, which is the increase in gas pressure, which is 30 cm of water. I need to divide by 2. So on this side, it will increase by 15 cm. And on this side, it will decrease by 15 cm. And the difference will then give me an additional increase in 30 cm of water. Okay, for the pressure. That is why this side it dropped by 15, this side it increased by 15.